Okay, let's pick back up again. There's only one more topic left in chapter number 2, which is maximum power transfer theorem. And so let's go ahead and take a look at that. One note. Okay, maximum power transfer theorem. Maximum power transfer theorem simply states that in order for maximum power to be transferred from the source to the load, the Thevenin resistance of both must be the same. Okay, Thevenin resistance must be the same. It is also known by another term known as impedance matching. Okay, impedance matching. Anyone ever install, like buy their own speakers and install it in a audio system? Has anyone ever done that? If you go online, and I always say go online because its information is freely available, but you could look at any manual, any specification for any speaker or any audio amplifier. It'll always give you a impedance value. For simple terms, let me not use impedance, let me use the term resistance. It will always state a resistance value. So an amplifier connected to a speaker or an audio system connected to a speaker will have some resistance, output resistance for this AVR output, and then the input specification of the speaker. The speakers typically would be 8 ohm resistance, and the output of the amplifier would also be 8 ohms. And so if you are buying speakers off the shelf to connect to your amplifiers, you always have to match the output resistance of the amplifier to the resistance of the speaker. Okay, and that ensures that maximum power is transferred from the AVR to the speaker. Okay, and that technical concept is basically coming from the Thevenin resistance. When the Thevenin resistance of the load matches the Thevenin resistance of the source, in this case, the first circuit, then maximum power can be transferred. Caveat is that maximum power does not equal maximum efficiency. Okay, maximum power does not ensure maximum efficiency. It's impossible to have that. I think almost impossible to have that. If you want maximum power, power losses will occur. You're not efficiently using the energy. Okay, so maximum power transfer does not take place at maximum efficiency. So in some, depending on your application, sometimes we want maximum efficiency, sometimes we want maximum power. Very simple analogy can be made in terms of vehicles. Whether your vehicle is gas powered or whether it's electric vehicle, if you, let's say you pump the pedal or pump the gas, accelerate and speed up very, very quickly, what are we doing? We are burning a lot of fuel, whether we are actually using up stored battery energy or whether you're using up gasoline or diesel, you're using up a lot of fuel to get a lot of power, right? So maximum power transferred, but it's not at maximum efficiency. If you want maximum efficiency, then you ease off on the pedals. And with modern cars, you have this technology that monitors how your batteries are being used or how your fuel is being used. And you're able to monitor in real time your fuel efficiency. So again, kind of like a rough or crude analogy, but I think it works. So in order for maximum power to be transferred from the source to the load, Thevenin resistance must match. And that's where maximum power transfer occurs. Okay. All right, let's take a pause, think over that. Let me know if you have any questions. Any questions? Yeah, same thing, right? I mean, you're using up more energy. Okay, so the question being asked is if we accelerate faster in an electric vehicle, the battery range degrades, right? Is that your question? No, it requires more force and more energy to accelerate faster. So you're using up the energy that is stored in the battery. Yep. And so and again, that's why I said, whether it's an electric vehicle or whether it's a gasoline powered vehicle, you require more fuel, you require more energy, right? It's the same thing with the electric vehicle also. And another analogy can be made. There's this example, I don't know, you may or may not have heard of it. There's a triangle: quality, cost, and time. You can have two of the three, but you can never have all three together. You can save time if you go low quality or low cost. If you want speed, you can compromise on quality, but you cannot compromise on cost. If you want high quality with the least amount of time, is going to cost you a lot of money. So you can never have the best of all three. If you want good quality with low cost, it's going to take you more amount of time. And so again, if you want to accelerate faster, it's going to cost you in terms of energy. Okay, let's see. Why is that is the end of chapter 2. So this was resistive circuit analysis. From this point on, we will go into capacitors and inductors in chapter 3 and chapter 4, and then AC analysis from chapter 5 onwards. Now, chapter 3 is completely about DC, and well, it introduces the topic of capacitors and inductors, which you have studied in physics for a little bit, but I will go in depth and I will cover all the equations. The big difference between a capacitor and inductor versus resistors is that resistors are not energy storage devices, whereas capacitors and inductors are energy storage devices. Okay. So again, let's bring this up. So inductors and capacitors are energy storage devices. Inductors are represented with the uppercase L. Capacitors are represented with the uppercase C. And they are both energy storage devices. Whereas a resistor does not store any energy, it simply transforms it. Resistors take electrical energy and transform it into thermal energy and dissipate it as heat. Capacitors and inductors will receive the energy, they will store it, and they will release it back into the circuit at a later point in time. This energy transfer, of course, there's some heat loss that occurs, but primarily, but more importantly, they will receive the energy and they'll release it back in the circuit. Now, two things. I stated they're energy storage devices. So the energy storage and the energy release takes a fraction of a second, depending on the size of the capacitor and inductor and depending on the circuit conditions. Okay. Think of it as a bucket of water that you're filling up. Smaller the size of the bucket, the faster it will fill up. The larger the bucket, the longer it will take to fill up. And of course, it also depends on the size of the pipe and the fluid flow rate. Okay, so the capacitor and the inductor is like a bucket of water. you're filling it up with water. That is the energy that is being transferred into the component. And then that depends on the size of the bucket, as well as the size of the pipe, as well as the fluid flow rate. And releasing it back into the circuit, again, takes a fraction of a second. We're talking about milliseconds or even microseconds. Okay. The other part of it is that energy transfer cannot take place instantaneously, right? Thanos cannot snap his fingers as much as he wants and transfer the energy instantaneously. It takes a certain amount of time for the energy to be transferred into the capacitor and inductor, and a certain amount of time for the energy to be transferred back into the circuit or released back into the circuit. So the energy transfer portion of analysis is what we will study in chapter 4. Okay, because that analysis is fleeting, it is momentary, it is transient with respect to time. Okay, it does not take place instantaneously. It takes a finite amount of time, and that we will study in chapter 4. Chapter 3, we will talk about inductors and capacitors in general. Okay. So let's talk about inductors first. We'll talk about magnetic fields and how and why it is important. Magnetism plays a very important role in modern electronic devices. It has always played a very important role. Okay, it is very integral. It is highly integral to almost everything that we use today. Some of the most common examples, of course, are in AC power generation and transmission. Without electromagnetism, we would not be able to generate the electricity that we use in everyday life. Much closer, if you have a smart device which has wireless charging, basically like a smartwatch with wireless charging or a smartphone or a tablet with wireless charging, there's an inductive coil in the back of these devices. Again, electromagnetism. Okay, so magnetism in general is very important. Electromagnetism even more important. And as I said, common examples are generators, motors, transformers, without which modern electronic devices would never work. Electromagnetism has been researched for several centuries. One of the most prominent ones was around the early 1800s with Ampere, Gauss, Maxwell. They laid the foundation for electromagnetic theory, and much of the foundational work was done during that period. Now, magnetic field occurs in every electrical conductor that carries an electric current. You take any piece of wire and you send an electric current through it, it will have a surrounding magnetic field. And that magnetic field will have flux lines. These flux lines can be noted by the right-hand rule. The right-hand rule states, if you hold a conductor in the palm of your hand and you point the fingers around, or you wrap your fingers around it and you point your thumb outwards, then your thumb points towards the electric current and the fingers point in the direction of the magnetic flux lines. Okay, so this is the right-hand rule. Now, typically we would say that the magnetic flux lines have no beginning and they have no end because they are circular. Circular or completely wrapped around closed loops. If you take that current carrying coil, a current carrying conductor, and we turn it into a coil or a loop, then the flux lines align and point outwards from the center of that loop. Okay. If you take that same conductor and you convert it into multiple loops, a spiral loop, then the flux distribution aligns towards each loop as well as through the center of that entire coil, creating a sort of a magnetic field that mimics an actual magnet that has a north pole and a south pole. Okay, hence noted by the N and the S. This magnetic field is very weak. Okay, depending, of course, on the value of the current and the size of the coil. It is very weak. It is not strong, but it mimics a magnet. Mimics a magnet. And then what researchers discovered was if you inserted a magnetic material, ferromagnetic material, through the center of the coil, that magnetic field would become very strong. And that is the principle, that is the working principle of an electromagnet. Okay. If you insert a ferromagnetic material through the center of an electric coil, the magnetic field that is established around it becomes very, very strong, similar to a natural magnet. As long as current is flowing through the coil, it behaves like a magnet. When the current is switched off, the magnetic field disappears. Again, this is the working principle of an electromagnet. Let's take a pause. Let me know if you have any questions. It'll still be a magnetic field. No. So if I understand your question correctly, is if you remove the core material, the magnetic field, see, the answer would be if you remove the core material, the magnetic field will still be there. It will still behave like a magnet, but it will be very, very weak, because in the absence of a ferromagnetic material, the core material is simply air. And so here's the follow-on concept a little bit. A ferro or a magnetic material is so called because the magnetic flux lines can be established through it with ease. Even air can be said to be a magnetic material, but it cannot establish the magnetic flux lines with ease. It would be similar to kind of like an electrical conductor. Everything can be a conductor, but they would not be as good of a conductor as, let's say, a metal. Okay. At some point, dividing the conduction and the non-conducting portion, we'd say above this line is an insulator and below this line is a conductor. So we can establish a magnetic flux line with every material. We define the materials where we can do it with ease as magnetic materials and the rest as non-magnetic. Yes. So it's not an electromagnet so much as it is has two wireless coils or two inductors coming in close contact, and then the electromagnetic field of both inductors, they link up. And that is the principle of a transformer, actually. So transformer is two inductors wound tightly around the same core, such that the magnetic fields of both inductors are linked up. And then again, there's a lot of technical stuff that goes into that, but that's essentially what it is. So you have every inductor has a magnetic field, and when you bring them in close proximity, the magnetic fields link up. The energy from one can be transferred to the other. So the question was about wireless charging, and the answer is when you have a wireless charging plate, that wireless charging plate is actually connected to a USB port. That USB port will supply the energy to the wireless charging plate. The wireless charging plate has a coil. The coil will have a magnetic field. The back side of your smart device, whether it's a watch or a smartphone, will have a coil. And when you place it on the wireless charging mat, the coils of both will be interlinked. The electromagnetic field of both coils will become linked, and the charging mat will supply the energy into your smart device through that coil. And the coil inside your smart device will convert that magnetic field energy into electrical energy. There are losses that occurs because this energy transfer taking place, so it gets hot. And to limit the heat or the thermal losses, the current is kept low. If you make it really high, it's going to get really, really hot and burn everything out. So wireless charging is inherently slower than wired charging. It's all AC, yes. For DC, an inductor would behave like a short circuit. There will not be any magnetic field. It will just store it and pass everything through. You can buy these. So I've purchased. Let me bring it up and see if I can find it. So people do all kinds of things. People have been doing all kinds of things. Several years ago, I saw here. So you're going on a tangent, but I think this is interesting for students to see. So you can buy these off of eBay for real cheap. You can buy it from anywhere. And people, build like custom tables or cutouts in their tables, like side tables and stuff. And they would install these coils. They would buy these coils for like $3-4 and install these coils inside their tables. So it doesn't look like a mat. You just place it on your table and be like a very thin wood or paper covering on it. And they can just place, they would show off to their friends or their family. They say, hey, I put my phone down here and it's charging wirelessly. And it'd be pretty neat. So if you do like an internet search, people have, so this is like a 5-coil, there's like 3-coil ones. And people do, all kinds of things with this. There's lots of hobby enthusiasts who have been doing this. Incidentally, this technology has been around for a long time. The earliest smartphone that I ever saw in person, which I still have that, was a Samsung Galaxy S3. S3 was like, I don't know, 2007. No, not 2007, 2010 perhaps, 2009 or 10. And it had a wireless charging coil in the back. It had that capability as far as like 14 years ago. Anyway, any other questions? I think this is all interesting to me. You could buy round. I bought like these round chargers from eBay for like $4 or $5, like many years ago. Yeah, and they work. They work very well. All right, let's see. Okay, so that was the working principle of an electromagnet. So there we just define inductor. Inductor is simply a coil of wire that flows. We've established that when current flows through a coil of wire, it establishes a magnetic field. The actual component is referred to as the inductor, and the phenomena is known as inductance. Okay. Again, they only store and release energy. They do not have any energy of their own. We use inductors, we use coils to actually generate our electricity, right? We have a coil that is wound and moving in a circular fashion inside a rotating magnetic field, and that is what generates AC electricity. Okay, so that is an inductor. Inductor is a passive component. It is noted with a spiral, right? Usually don't draw it like this. It's a spiral, doesn't matter how you draw it. Excuse me, and it follows the passive reference configuration. Okay, it follows the passive reference configuration, meaning current goes from plus to minus, high to low. High to low. Inductors are referenced with an uppercase L and has unit of Henry. Named after, does anybody know? American physicist Joseph Henry. So 1 Henry. Okay. Now, the technical definition of an inductance is 1 Henry of inductance is the level of inductance that will produce a change, that will produce 1 volt across its terminals for every change of 1 ampere in current, or every change of 1 ampere per second in the current that is flowing through it. Okay. So again, current flows through an inductor, establishes a magnetic field. When you try to change the value of this current for every 1 amp per second change in current that takes place, if it establishes 1 volt across those terminals, we say that the inductor has 1 Henry of inductance. In real life, inductors are not 1 Henry. 1 Henry is huge. Real life inductors are very, very small in size and value, typically in the order of like millihenries or microhenries. Okay, millihenries or microhenries. So typical inductors are very, very small. Inductor construction, physical construction of an inductor is given by this equation right here. L is equal to mu, the Greek letter mu, mu, and square A over L. This L is lowercase l. Lowercase l. Okay. Actually, it causes confusion. So the uppercase L stands for inductor in Henry. Mu is the permeability, and that permeability is the product of mu 0 times mu r. Mu 0 is the absolute permeability. Whereas mu r is the relative permeability of the core material. Permeability of the material. All of the values would be given. So if I asked this in a quiz or an exam, I would give you the values for mu 0 and mu r and everything else. Okay. A is the cross-sectional area of the core that comes from the diameter or the radius of the core. That's from here. And L is measured from the beginning of the first loop to the end of the last. Okay, it's the length of the core of the coil. It is not the length of the wire. Obviously, if you take that spiral wire and you unwind it, that length is going to be much longer than the length of the actual coil. So again, it's important to note the L is from the first loop to the end of the last one. All right, let's take a pause. Let me know if you have any questions. Yes. No, wound. The wound coil. Wound length. Any other questions? Okay. Here are some examples, real life examples of real life inductors. And we'll talk about that later, but I want to get into the voltage and current equation for an inductor. Okay, so inductors and capacitors are now, we journey into the time domain. Remember I said, the energy transfer does not take place in an instant. It requires a certain amount of time for the energy to be transferred. So the voltage and current equations of capacitors and inductors are time dependent. So the primary equation for an inductor is V equals L di over dt. Voltage is the product of the inductor and the time derivative of the current. As the current changes, the rate of change of current, that gives you the voltage. Okay, so depending on how fast the current changes, the voltage across the inductor would change. So V equals L di over dt. If you wish to find the current, then you integrate both sides. You got integral of the voltage, integral of L di over dt. And so I would be equal to 1 over L integral of the voltage. Okay, I will explain the rest of the terms when we actually get to an example problem. Okay. Now I want to talk about this term, di over dt, rate of change of current. What does it mean? Okay, is how fast the current is changing, the input current, how fast it is changing. For an applied DC current or DC voltage, it has a fixed value. What is the derivative of a constant? It's right there on the screen. Zero. Derivative of a constant is zero. When a current is flowing through an inductor, if it changes its value, then the inductor opposes it. However, once it reaches full charge and it becomes constant, then the voltage across the inductor is equal to zero, because the inductor is now behaving like a short circuit wire. Current is simply passing through. Okay, it is simply passing through. Now, this also relates to AC input, and I'll explain how. So when you apply a DC current, let's say the inductor does not have any stored energy. You apply a DC current. When the current starts flowing through the inductor, energy is being supplied to the inductor. The energy cannot take place in, energy transfer cannot take place in an instant, cannot go from 0 to max or full in an instant. It'll take some time for the energy to reach maximum charge. Okay. If this is time and this is the voltage or the current or the energy, is always an exponential. This is something we'll look in chapter 4. But once it reaches maximum charge, what will happen? The magnetic field is being established, right? Current is applied, magnetic field is established, it'll store the energy. Once it reaches maximum capacity, meaning the magnetic field has stored as much energy as it can, from that point on, current is allowed to pass through unopposed. There is no opposition. Now, what happens is this magnetic field gives rise to an opposing EMF. EMF is another word for voltage, electromotive force. This voltage is opposite to the flow of the current. Now, if you try to change the input current, that magnetic field is going to oppose any change in this incoming current. And when it opposes, it is not direct opposition. Again, when you apply current to an inductor, there is no resistance, there is no opposition to the input of that current. But when you try to change that current, that change is being opposed. And that is something we will study in chapter 5, which is AC analysis. But I do like to point it out here, because at the same time, you're pointing about DC. So if it's DC, once it reaches full charge, inductor behaves like a short circuit, allows DC current to flow through unopposed. When it's AC, it opposes any change in the incoming input. It's a lot of information. So let's take a longer pause You think over that and let me know if you have any questions. Any questions? Okay. All right. Let's see. Power and energy. Power for a inductor still follows the same equation, P equals VI. So the standard gives you V is L di over dt. Simply plug that into the equation and you obtain power P is Li di over dt. When you integrate the power and you find the energy, which is lowercase w, it gives you half Li square, square of the input current times the inductor divided by 2. Okay, any questions about the inductor? Let's see. Oh. Any questions? Okay. Capacitors are nothing but two parallel plates separated by a insulating material. The two parallel plates are conductors, and this is the insulating material. Symbol for a capacitor is typically two parallel lines of equal length. They are not polarized except for an electrolytic capacitor. Capacitors are also passive components. You can connect them either way. Current flows from high to low. So once you charge up a capacitor, current will be flowing from high to low, plus to minus. Okay. Okay, capacitor charging. If you take a capacitor, two parallel plates, and you connect it to a, let's say, a battery source is Vs. Switch here simply indicates at some point in time, you're going to flip the switch. At the beginning, capacitor did not have any charge, so it was 0 volts. It was 0 volts. Now, the symbol of the capacitor, as I just stated, was two parallel lines. Oftentimes, you also see a symbol with one horizontal line, meaning one flat line, and one concave line. Typically, we just see two parallel lines, two straight lines. That's the most common one. When you connect a capacitor to a voltage source like this one, there is a charge imbalance. The two plates are separated by an insulating material. And here's where it gets a little confusing. When you connect it to the positive terminal and the negative terminal, because of the charge imbalance, electrons in the wire and the plate, the top plate of the capacitor, are attracted to the positive end of this battery. And they start moving in this direction. When an electron moves out, what is left behind in its place? An equal but opposite positive charge. So for every electron that moves away from the top plate, a positive charge appears on that plate. Okay. Similarly, on the other side, due to the negative end of the battery, electrons in the wire are, are repelled. So that causes a buildup of negative charge on the other side of the capacitor. The difference in electric potential between the two plates can be measured as the capacitor voltage VC. Capacitor voltage VC. And here's where it gets confusing. We have continuous motion of electrons, right? We have continuous motion of electrons in a counterclockwise motion. However, they are not moving through the plate. This is an important distinction. Physically, there is nothing that is going through the two plates. It is separated by an insulator. The two plates are separated by an insulator. They are not going through the plate. Yet, there is a motion of electrons in the circuit. And so we say that there is current flow in that circuit, and we refer to it as capacitor current. And we also use the words current flowing through the capacitor. But again, I want to emphasize the two plates of the capacitor are separated by an insulating material. So electrons are not flowing through the capacitor, yet we still use the term current flowing through the capacitor. Okay, so let's take a pause while you think about that. Any questions? Any questions at all? Okay. So as I was saying, capacitor voltage can be measured once it reaches full charge. There is no more charge imbalance. VC will reach a level that is equal to VS, the supply voltage. Once that is equal, there is no more charge imbalance and the electrons stop flowing. The electrons stop moving. Once they stop moving, we say that it has reached full charge. And because the electrons stop flowing, current is equal to 0. Current is equal to 0. And you can remove the capacitor from the circuit and it will hold its charge indefinitely. Of course, that's an ideal capacitor, not real life capacitors. Real life capacitors will discharge slowly but surely through the air and through the insulating material itself. Okay, so it's not going to hold its charge indefinitely. But there are internet videos where people will charge a huge capacitor together. I mean, huge capacitor, take it out of the circuit and short the two leads together. And so you have a spark. All of the energy is released in an instant, and that creates a spark. So again, capacitor is two parallel plates separated by an insulating material. When you connect it to a DC source like a battery, Then charge builds up due to the flow of electrons. Once it reaches full charge, there is no more charge imbalance. Voltage across the capacitor equals the supply voltage Vs. And once that happens, we say the capacitor has fully charged. And a fully charged capacitor acts like an open circuit. Here, let me go here. Fully charged capacitor, it acts like an open circuit. So inductor behaves like a short circuit, capacitor behaves like an open circuit. The primary equation for a capacitor current is I equals C dV over dt. I equals C times dV over dt. And at this point, I would like to point out some notation differences or similarities, if you know. Let's take a pause. Let me know if you have any questions. Yes. Charge. I will talk about that later. Yeah. So capacitors and inductors are very similar to each other, but they're also opposites. Okay. Capacitors store charge in an electrostatic field or an electric field, and inductors store the charge or the energy in an electromagnetic field. So they're very similar to each other in terms of operation, but they're also highly opposite. So one thing I'd like to point out is about the notations. So for inductor, the voltage was L di over dt. For capacitor, the current is C dV over dt, right? Rate of change of voltage, rate of change of current. Now, if you notice here in the capacitor equations, this is on purpose. I show it as a function of time. This is to show students that different notations can be used for the same thing. So this I can write as V of t is L times di of t as a function of time. And same thing here. C times V of dt. So oftentimes you would see references from different authors or different books or different papers with or without the t as a function of time. And they are all acceptable and same to each other. Even further, if you have more than one capacitor or more than one inductor in the same circuit, you would note it with a subscript, meaning the inductor would be a VL of t, in the capacitor would be IC of t. This could be VL of t or VC of t or IL of t and IC of t. If you have more than one inductor, it would be L1, L2, L3, capacitor C1, C2, C3. Okay, they're all pretty much the same. There's no difference between them. So sometimes it'll just be VC, VL without the t or function of time. Sometimes it would be a function of time, but they all mean the exact same thing. All right, let me know if you have any questions. Okay, we'll end class here today. Pick up here again on Wednesday. We'll wrap up chapter 3 on Wednesday with last bit of theory and a few examples.